Selecting the right motor for a pump is one of the most important decisions in any pumping system. And yet, many pump failures are not actually caused by the pump itself. They happen because the motor was selected incorrectly. Wrong voltage, incorrect frequency, or improper power sizing can lead to overheating, unstable performance, excessive energy consumption, and expensive downtime. So in this video, we'll explain how to select the right pump motor based on three key factors: voltage, frequency, and power. Whether you work with centrifugal pumps, slurry pumps, sewage pumps, split-case pumps, or multistage pumps, this guide will help you improve efficiency, reliability, and long-term performance. Let's get started. First, let's talk about why motor selection matters. The motor is what converts electrical energy into mechanical energy to drive the pump impeller. If the motor and pump are not properly matched, several problems can occur. The motor may overheat. The pump may vibrate excessively. The system may consume more electricity than necessary. And maintenance costs can increase dramatically. A properly selected motor helps ensure stable operation, lower energy consumption, longer equipment life, and better hydraulic performance. That's why motor selection is such a critical part of pump system design. Now let's look at the first key factor: voltage. Voltage refers to the electrical supply available at the installation site. Common industrial motor voltages include 380 volts, 400 volts, 415 volts, and 460 volts. In residential or small agricultural applications, single-phase voltages like 110 volts or 220 volts are common. Industrial pumping systems usually use three-phase motors because they are more efficient and provide more stable operation. Choosing the wrong voltage can create serious problems. Low voltage increases current draw and heat generation. High voltage can damage motor insulation and windings. So before selecting a motor, always verify the available power supply at the site. Check whether the system is single-phase or three-phased. Confirm the exact voltage. And make sure the electrical supply is stable. Another important consideration is cable distance. If the pump is installed far away from the power source, voltage drop can become a problem. This is especially common in irrigation systems, mining operations, and borehole pump installations. In these situations, proper cable sizing becomes extremely important. Next, let's talk about frequency. Frequency is measured in Hz, or Hz. The two global standards are 50 Hz and 60 Hz. This is very important because motor speed depends directly on frequency. A 60 Hz motor runs approximately 20% faster than a 50 Hz motor. And when pump speed increases, flow rate, head pressure, and power consumption also increase. That means using the wrong frequency can overload the motor and damage the pump. For example, a pump designed for 50 Hz may consume significantly more power when operated at 60 Hz. Incorrect frequency can lead to overheating, excessive vibration, bearing damage, and even cavitation. This is especially important for export projects. Different countries use different electrical standards, so frequency must always be confirmed before production and installation. Whenever possible, dual-frequency motors are a good solution for international projects. Now let's move to the third factor: motor power. Motor power is usually measured in kilowatts or horsepower. The motor must provide enough power to drive the pump safely under all operating conditions. Pump power depends on several factors: flow rate, head pressure, liquid density, and overall system efficiency. Many buyers think a larger motor is always safer. But that's actually a common mistake. Oversized motors often operate inefficiently. They consume more electricity, increase operating costs, and reduce overall system efficiency. Instead, the goal is to select a properly sized motor with a reasonable safety margin. For clean water pumps, a safety margin of around 10 to 15% is usually recommended. For slurry pumps or heavy-duty industrial applications, the margin may increase to 20 or even 30%. For example, if the calculated pump power requirement is 45 kilowatts, a 55 kilowatt motor may be an appropriate choice. Another important concept is the service factor. The service factor indicates how much temporary overload a motor can handle. For example, a 50 horsepower motor with a service factor of 1.15 can briefly handle a higher load. But motors should not continuously operate above their rated power. Doing so will reduce motor life and increase heat generation. Now let's discuss some additional factors that affect motor selection. First is pump type. Different pumps create different load conditions. Centrifugal pumps increase power consumption as flow increases. Slurry pumps require additional power because they handle abrasive solids and high-density fluids. Positive displacement pumps require stable torque output. So motor sizing always depends on the specific pump application. Fluid properties also matter. Thicker liquids require more power. Higher density fluids increase motor load. Temperature, viscosity, and solid content all affect motor selection. This is why industrial slurry pump motors are often much larger than standard clean water pump motors. Starting conditions are another important consideration. Some pumps require high starting torque. Examples include large slurry pumps, vertical turbine pumps, and high-head multistage pumps. In these cases, soft starters, or variable frequency drives, also known as VFDs, are commonly used. Speaking of VFDs, let's talk about their benefits. A variable frequency drive controls motor speed by adjusting frequency. This allows the pump system to operate more efficiently. Benefits include energy savings, soft starting, reduced water hammer, lower mechanical stress, and better flow control. VFDs are widely used in HVAC systems, irrigation systems, water supply systems, and industrial process applications. For many modern pumping systems, using a VFD can significantly reduce energy consumption. Another important topic is motor efficiency. Modern industrial motors are classified using IE efficiency ratings. These range from IE1 to IE4. Higher efficiency motors reduce electricity consumption, generate less heat, and typically last longer. Although premium efficiency motors cost more initially, they usually save substantial operating costs over time. For continuous duty industrial pumps, IE3 or IE4 motors are often the best long-term investment. Now let's look at some common pump motor selection mistakes. One major mistake is ignoring actual operating conditions. Ambient temperature, humidity, dust, and altitude can all affect motor performance. Another mistake is selecting a motor based only on rated power while ignoring torque requirements and starting current. And of course, using the wrong voltage or frequency is one of the most common issues in international pump projects. Always verify local electrical standards before purchasing equipment. So what's the best approach? Always review the pump performance curve. Work with experienced pump manufacturers. And focus on total cost of ownership, not just initial purchase price. A cheaper motor may cost far more over time through higher energy bills and increased maintenance. The right motor selection improves efficiency, reliability, and long-term system stability. To summarize, when selecting a pump motor, always confirm the correct voltage, the correct frequency, the required power, the motor efficiency class, starting conditions, and the actual operating environment. A properly selected motor helps reduce energy costs, improve pump performance, and extend equipment lifespan. And in industrial pumping systems, that can make a very big difference. Thanks for watching. If you found this video helpful, don't forget to like, subscribe, and share. And let us know in the comments. What is the most common motor selection problem you encounter in pump projects? See you in the next video.